In the previous videos, we've taken a look at what happens to an object if it is undergoing an acceleration, but we ducked the question of what is making it accelerate in the first place. It turns out that we attribute accelerations to the action of forces on objects. And to that end, we're going to iteratively define the idea of a force. And so for our initial definition, we will sort of build off of our intuition on this. So intuitively, we know it's some sort of a push or pull on an object. We also know that it is a vector quantity. Sorry about that. Because it has both a magnitude, how hard do I push it, and a direction, which way do I push it. And we know from our practical experience that both how hard and which way matter for the motion of the object. We also know that it requires an agent. What this means is something has to be doing the pushing or pulling, some other object. And we know from our experience that some forces seem to be long range. For instance, gravity seems to attract over distance. Then we also know that I don't have to have a magnet, say, touch an object in order to pick it up. It could just be nearby and attract it. Those would be examples of long-range forces. We also intuitively know that there are what we call contact forces. For instance, we know intuitively that if I'm sitting on my chair, the chair is only going to push up on me as long as I'm in contact with the chair. Once I get out of the chair, it doesn't push on me anymore. Similarly, if I throw a ball, we require contact. I can't push on the ball after the ball has left my hand. So those kind of forces we call contact forces. It'll turn out that we can blame the contact forces mostly on the electric force due to entire collections of molecules interacting with entire other collections of molecules via the electric force. But we'll get there. A little more reflection might not be immediately obvious at first, but forces arise from the mutual interaction of objects. So what do I mean by that? What I mean is that forces are never a one-way street. If I push on a wall, I'm feeling that, right? It's not because I'm pushing on myself, it's because the wall is pushing back on me. Now, because the wall is so much more massive than me, we'll see that that means that I'm not exactly going to be accelerating the wall at anything that matters. But I'm pushing on the wall, and whatever happens to the wall is because of me. But the wall pushes back on me, and the nerves in my hand feel that push back from the wall. So we get that the interactions between the two objects are mutual. Now, physicists have spent an awful lot of time analyzing forces, and we've boiled it down to three fundamental forces of nature. And you may say, wait a minute, I thought there were four. Just bear with me. So we'll start with gravity. So with gravity, it is we know that it has, or we think it has an infinite range. So this means that every object in the universe interacts with every other object in the universe via gravity. We also know that it is absurdly weak compared to the other forces. In case you don't believe me on that, think about drinking your favorite beverage. When you lift up your glass, it turns out that that force of friction between your hand and the glass, that is a bulk interaction of the electric force between molecules in your hand and molecules in the glass. It also turns out to be an almost completely canceled out version. It's operating at a minuscule fraction of its full strength. And even so, that is more than enough to defeat an entire planet's gravity pulling down on your drink. This is an open puzzle in physics. The other forces of nature are within about a factor of 1,000 or so of each other. But gravity is not just not in the same zip code, it's not in the same metaphor. It is so far weaker than the other forces that this is a head scratcher for us. However, that being said, it turns out that over long scales, like say planets, the solar system, the galaxy, that kind of thing, over long scales, it's significant. And this is mostly because for the other forces, there are mechanisms that tamp down their effect. Okay. Much, much stronger than gravity is what gets called the electroweak force. Now, you may not have heard it called that before. This is relatively new in the history of physics. Turns out that the electroweak force is a combination of the electromagnetic force and the weak nuclear force. Actually, let me talk about weak nuclear first because I have less to say about it. So it's a combination of the weak nuclear force and the electromagnetic force. In the 70s, a team, 3 different physicists by the names of Salam, Glashaw, and Weinberg, demonstrated that these two seemingly different forces, the weak nuclear force and the electromagnetic force, were actually 2 different aspects of the same interaction. However, in practical life, unless you're worried about things happening in a high energy particle accelerator or something like that, the weak nuclear force will act very distinctly from the electromagnetic force. And so in most situations we can go ahead and pretend that they're different. Now the weak nuclear force has a short range, very short, not basically on the order of the width of a proton. And the main thing that its main claim to fame is that it controls certain nuclear decays. Certain. Probably the most famous of these is beta decay. This is the, oops, CAY. beta decay is at the basis of things like carbon-14 dating and stuff like that. Okay, that's about all I have to say about the weak nuclear force in this context. The other aspect of it, which, like I say, for practical purposes we can treat as a different force, is the electromagnetic force. Now, with the electromagnetic force, things we know about it, it also has an infinite range. And it's pretty strong. Not quite as strong as the weak nuclear force, but a lot closer to that than it is to gravity. It's significant over medium scales. Let's give you a little more space there. So for instance, like an atom or something like that. And this has to do with the fact that the electric force has both positive and negative charges. So, and because the opposite charges attract, if I have a whole bunch of, say, positive charge sitting somewhere, it'll attract negative charges nearby, or vice versa. So the upshot of that is that you tend to get collections of opposite charges fairly close to each other, for instance, an atom. And then if you happen to be far away, the fact that the opposite charges are so close to each other means that the contributions to the forces from those kind of charges almost cancel out. And so that's why, like on an atomic scale, a molecular scale, things like that, the electric force is a big deal. Past that, it starts to fade away. I've already mentioned before that it's the main player in contact forces, in fact, specifically the electric force aspect of it. And historically, a similar thing to the identification of the electroweak force happened in the 1870s. James Clerk Maxwell followed up on some initial hints from Michael Faraday, but Maxwell did the heavy lift here. And he showed that the seemingly different electric, LECTRIC, and magnetic forces were actually two different aspects of the same thing that we call the electromagnetic force. Now it does turn out that in a lot of cases it turns out that you can pretend that the electric and magnetic force are two totally separate things, much like we do where we pretend the weak nuclear force is a totally separate thing most of the time. But there are times where you actually do care. So you have to be a little more careful there, but more on that in a different course. But kind of keep this in the back of your mind. In the 1870s, these two seemingly different forces were shown to be two aspects of the same thing. And in the 1970s, these seemingly two different forces were shown to be two aspects of the same thing. Okay. The strongest of the forces out there is one called cleverly, the strong nuclear force, to distinguish it from the weak nuclear force. And for it's short range, not as short as the weak nuclear force, but the strong nuclear force cannot make it all the way across a self-respecting nucleus. Small nuclei it can cover across, but bigger ones it can't. It is the strongest of the forces that we know of. And it holds particles called quarks together to make things like protons and neutrons. And it also holds those protons and neutrons together to make nuclei. So it holds nuclei together. Now, keeping in mind the history of things, we saw in the 1870s, the electric and magnetic forces were demonstrated to be two aspects of the same thing. And then a century later, the electromagnetic force and the weak nuclear force were shown to be two aspects of the same thing. So it'd be natural to ask, are these three forces aspects of the same thing? And the answer is we don't know. There are tantalizing hints that it may be a combination of looking at the world of the extremely small, looking at subatomic particles, sort of thing that gets done at, say, the European Center for Nuclear Research, CERN, or Fermi Lab in the United States, located in Batavia, Illinois. Those researchers probe the world of the extraordinarily small. And then if you combine that with data on things like the expansion rate of the universe, there are some tantalizing hints that possibly these three forces are all aspects of the same thing. Or maybe not, but there are hints that they may be. And so researchers have been looking to see if they can develop a model where you could show that these three forces are aspects of the same thing. If you've heard of string theory is an attempt to do that. There are other models out there as well. So anyway, that's very much of a watch this space kind of thing. Now where we're going to go with this for the moment, gravity we'll treat later on. But for the moment now, I would like to go and take a look at the contact forces. So we'll sort of do a bit of a taxonomy of them and try to come up with a bit of a model for how they work. So all of our contact forces, like I said, are bulk models for the electromagnetic interaction. And so the first of these I'd like to take a look at is what's called the normal force. Now, this is a very bizarre name, I will agree. You know how sometimes when you look in the dictionary, you'll see two entries that are spelled the same, but instead of just being given separate definitions under one entry, they're actually given two totally separate entries. And they'll usually like put a superscript 1 after one of the entries and a superscript 2 after the other. This usually indicates that although the words now look and sound the same, the path by which they developed into English were radically different paths from radically different roots. This word normal, if you look in the Oxford English Dictionary, is normal 2. Normal 1 is the usual one where you look it up and it means not messed up. Normal 2, which is the normal we're using here, means perpendicular to a surface. So this, for instance, is the force that your seat exerts on your rear end to keep you from falling through the seat. So how does the seat know how to do that? Well, to that end, what we can do is we can imagine looking at a bunch of atoms. And it turns out far more ridiculously accurately than it has any right to be, you can model the electric interactions between all the atoms in a crystal or something like that as basically as if the atoms were tied together with springs, which is what you're seeing me do here. Here, let's just start dropping them in like this. Oops. There we go. And so when an object is, so what happens is, say if you sit down on your seat or something like that, the molecules in your backside are, via the electric force, going to start interacting with the molecules in your seat. There we go. All right, that's not too bad. And so when they interact with molecules in the seat, what happens is you slightly deform the seat. So if they were where I drew it in black, now these molecules might be dislocated a little bit, like that. So that's going to have the effect of making this bond longer. And it'll have the effect of, say, making that bond shorter. Again, like this bond will get longer, that bond will get shorter, this one get longer, that one get longer, shorter, 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 like that. Well, the thing is like a spring, the bonds in a crystal or any other solid want to stay the length they were. And so these longer bonds will try to contract to pull the molecules back up, and these shorter bonds will try to expand to try to push the molecules back up. In the process, via the electric force, these molecules here are going to exert a push up on your butt. And so that's how the seat can push up on your butt to keep you from falling through the chair. Now, many of us have probably had the unfortunate experience of discovering, if you sit in a really old and really rickety chair, that sometimes the molecules in your seat give up. And this is true with a lot of these contact forces. Here, if I try to stretch these bonds too far, it'll become energetically favorable for the bonds to just plain break. And if you do that, then the object breaks, and then you do fall to the floor. But this is how the object knows how to push back. We're going to hold on friction until a later video. So for friction, I'll just say that this is a coming attraction. Mostly because it's a complicated enough model that deserves its own separate analysis. But we can look at, say, like tension or a spring force. They work basically the same, but there is one slight difference. So here, if say you pull on a rope, it's the same deal. Your molecules are all nice and spaced at their equilibrium spacings. And then when you pull on the rope, what winds up happening is you stretch out the bonds. They get longer. So again, same deal. As a result, the bonds will try to contract and pull the rope back to its original shape, exerting a force due to tension on the objects that the rope is attached to. With a spring, the same kind of thing happens, except you also allow for the possibility of the bonds to compress. And if that's the case, it'll try to return back to its original shape by trying to push the things that are doing the compressing out of the way. With tension, like with a rope or a string, that won't happen. Because of the details of the bond, what will happen is that the bonds will just stay the same length, but the molecules themselves will move off to the side. So if you ever tried to push on a rope, you see how it just buckles under. That's what differentiates tension from spring force. And before you get all cutesy with me and say, yeah, but you can totally push on a rope in winter. Yeah, you just pushed on an icicle, and that's something solid, and that's going to be more like our spring force again, rather than a true rope. Anyway, that will do it for our initial survey of forces. I will catch you all in the next one.